All right, so I'll begin by going through the answers to the quiz here. So this, we have x squared, that integrates to 1 cubed, x cubed. Square root of x, that's x to the 1/2, so that integrates to 2/3, x to the 3/2, plus a constant. Both of those are by the power rule. This one, the integral of sine is minus cosine. The integral of 3 to the x is 1 over log 3 times 3 to the x plus a constant. That's that one. Tangent squared, that one's a little bit sneakier. Here we need to remember there's an identity that connects secant squared and tangent squared. So this one's kind of a trick question in some sense. So remember, we all know sine squared x plus cosine squared x is what? Is 1, right? So if we divide that by cosine squared, what do we get? We get tangent squared, because sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And 1 over cosine squared, what's that? Well, that's secant squared x, yeah? So I can trade a tangent squared for secant squared minus 1. And that's helpful because secant squared x and 1, these are both functions that we can just straight integrate. So the integral of secant squared is tangent x, and the integral of minus 1 is just minus x. And of course, we have to add a constant. Now, I mean, this is probably the first time you've seen this for number 3. If you didn't get number 3, I would completely not be surprised, and like that's fine. But now you've seen it, right? This is like how we do tangent squared. This one is just an elementary one. That's inverse tangent of x plus a constant, right? And that one requires a little bit of algebra. So this one here, this is the integral of 1 over x plus 1 over x squared, right? Because x over x squared gives me 1 over x, and 1 over x squared was 1 over x squared. Now, the integral of 1 over x is the natural log of the absolute value of x. And the integral of 1 over x squared is minus 1 over x. So I'll put minus 1 over x plus a constant. So there it is. If you like, I can do, let me just show you the last one here a little bit better. 1 over x squared dx. See, that's the integral of x to the minus 2 dx, right? Which is, by the power rule for integration, x to the minus 2 plus 1 divided by minus 2 plus 1 plus a constant, which is, x to the minus 1 over minus 1 plus a constant, also known as minus 1 over x plus a constant. So that's why I put minus 1 over x here. So anyway, if you're not comfortable yet with these, it's understandable, but we need to work on them, right? So there are examples in the notes, which I haven't actually worked through in class. It would be helpful for you to work through, there's like 20 examples of integration in the notes. Like a good practice for you guys would just be to go through those and work them one at a time for yourself, right? You can watch me do it, but that's not going to make you learn it, right? Like you have to do it for yourself. Otherwise, it won't stick. That's just, Let's see here. So we're talking about definite integration today, right? And definite integration, we defined last class that the integral from a to b of f of x dx, what that is the signed area. It's the signed area bounded by y equals f of x. Technically, it's the limit as n goes to infinity of this, what's called the Riemann sum. This is what this is chopping the area up into the rectangles like we talked about last time and taking the limit of the number of rectangles going to infinity. So all of this is just to set the notation. The function which we're integrating is called the integrand. This is called the lower bound. This is called the upper bound. Altogether, this is a definite integral. In contrast, the quiz, I asked you to do what are called indefinite integrals. Indefinite integrals, you have plus a constant, right? The indefinite integral is an antiderivative. It's like the most general antiderivative, right? These two concepts are related in a surprising way by a fundamental theorem of calculus. So let me state the fundamental theorems of calculus for you. But, well, first things first, I need to tell you what are the properties of definite integration. So, and I'm not going to prove all these because, well, we just don't have time, and also I don't think the proofs are terribly helpful for your understanding of things in here. And so I'm going to save my energy proof-wise for the fundamental theorem. So the integral of a sum is the sum of the integrals, like this. We also have the property that if you have a constant times the function, you can pull the constant out. And finally, the one that's a little bit more interesting, 2, 3, the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Here, this assumes we have a less than c less than b. All right. Now, the proof of these given on like page 277 to 278 of my notes, and I'll let you read those if you're interested. But I think it's useful to, I suppose you could prove 1 and 2 here like graphically if you were so inclined, but I think the proof of 3 from a graphical perspective is just really, really simple. So if we have a function, right, and here's A, here's C, and here's B. So what item 3 here is saying is that the signed area, right, the signed area under the graph of the function from A to C, and I'll keep the function positive just for the sake of the signed area actually being area. So the area from A to C, right, it can be broken up into 2 pieces, namely the integral from A to C, which is this piece, plus the integral from C to B, which is that piece. So, I mean, of course this is true, right? Certainly the area, if you wanted to calculate the area under the curve, you could calculate this much, stop there, right? And then calculate that much and add them together. That'd be the total area. Like this is a basic property of areas. It should have this additive property, right? In fact, one of the things I should mention, I gave the definition for Riemann integral in terms of a continuous function. How would you integrate like a piecewise continuous function? What if your function is just continuous on pieces and it has like jumps? Well, you know what you can do? You can just integrate each piece of the function separately and then add those integrals together. That's how we do a piecewise defined function. All right? All of this said, if you look in my notes, there is a proof that's about a half a page to a page long to prove item 3. Like, it is a pain to actually prove this using the definition which is stated. And yet it's obvious, right? I mean, it's just geometrically obvious. So I'm going to try to save my energy for proving things which are not obvious today. Proposition 7.2.22. It has a few more properties of definite integral. So this is for f and g continuous. Continuous on the closed interval from a to b, and m a real number. All right, number one, if f of x is non-negative, if f of x is greater than or equal to 0, for all x in the interval from a to b, guess what? What can you say about the integral of f of x dx from a to b? And I think this proposition is really worth our time because it helps me to drive home a point. The definite integral is a number, all right? Definite integral is a number. If it exists, it is going to exist here. When we get to calculus 2, we talk about the possibility that a definite integral doesn't exist in the sense of it being an improper integration, but you know, we'll save that for next semester, right? So what can you tell me? If the function's non-negative, what can you say about the signed area? It's what? It's positive, right? This is also greater than or equal to 0. Exactly. So the integral preserves equality in that sense. Likewise, if f of x is greater than or equal to g of x for all x in AB, guess what? The integral of f of x dx from a to b is greater than or equal to the integral of g of x dx from a to b. All right? And then 3, I have a fairly careful proof of in the notes, but I'm going to prove it geometrically in class. But here's 3. If f is bounded by little m less than or equal to f of x less than or equal to big M, right? For x in the closed interval from a to b, then guess what? M times b minus a is less than or equal to the integral from a to b of f of x dx is less than or equal to big M times b minus a. And again, I'm going to give you a proof, well, really a plausibility argument in the context that the function's non-negative, because a picture will do here. All right, so what's going on? Here's A, here's B, right? And f of x is stuck between y equals little m and y equals big M, right? So like y equals little m, maybe it's here. All right? Y equals little m is like here. And then y equals big M is an upper bound for the function. It's up here, right? So, all right, so let's think about geometrically, what are the things that are here? So first of all, this guy, right, this blue box, that is M. What's this distance here? It is b minus a, right? So the area of the blue box is m times b minus a. That's the area of the blue box. The area of the yellow box, this guy, right? I won't shade it in, but the whole thing, right? That's over here. Because it's big M times b minus a, right? where's the function here? The function is bounded between little m and big M. So the graph of the function, it could be like this, I don't know, it's stuck between these two things, right? Whatever. That's the graph of the function, something like that, who knows? What's the area bounded by this? Well, I can shade it, it's this guy, right? So clearly, geometrically, the white shaded area must fall between the area. Tell me I didn't move the camera over here. Okay, good. I'll tell you, there's nothing worse than like going through a picture that you're happy about and then finding the camera's on the other board. But anyway, so it's clearly that this white shaded area is larger than the blue box, right? But it's smaller than the yellow box. And so this inequality holds. All right? So all of this just to say that the definite integral satisfies some very sort of intuitive, unsurprising things in terms of how it, interacts with inequalities. There's also a corollary here we could write, right? Here's a, by the way, observation. This is kind of just a dumb observation, but what's the integral from a to b of a constant dx? So this is the signed area of the constant from a to b, right? Can I draw the graph? What is it? Well, yeah, it's the signed area. In this case, let's just to keep it simple, let's suppose c is positive, so that signed area is just straight area. So we have y equals c, right? We have x equals to a, x equals to b. What's the area of this box? That by definition, the definite integral is the area of this box, which is what? What's the form? C, yes, exactly. C times b minus a. That's exactly it. So, hey, there's one. We can already do the definite integral of a constant. There's one. We can do that one, right? But we'd like to do more. Okay, so let's see. Excuse me. If we can anticipate some more here. So another example. So the purpose of this example is to try to anticipate the fundamental theorem of calculus part 2, okay? Or also part 1. But just here's an example. Suppose we have y equals x, right? Y equals x. Can you tell me what is the integral from a to b of x dx? So we're going to assume that a is like here, b is like here, just to keep it, Be the thing. The same thing. Well, I mean, the question is, what's the area of this region right here, right? What is that? Is that trapezoid or? So you could look at this as the big triangle, right? Minus the little triangle, right? Like the region's actually this guy right here, right? So this is 0, this is b, this is 0, this is a, right? What's the height of this one? This point up here, that's BB, I guess, right? This point right here technically is AA. Anyway, my point is that the height of this triangle is B, the height of that triangle is A, what's the formula for the area of a triangle? 1/2 base times height, right? So this should be 1/2 b squared, right? Minus 1/2 a squared, right? That's the formula for the area of that trapezoid, right? Can we see any kind of pattern going on here? Like, how about the previous example, the one with a constant? We also had that kind of b minus a pattern there, didn't we? See it? Let me put them both on the far board. So we have this, and I'll just put it right under it. We also have like integral of a constant dx from a to b is equal to, well, cb minus ca. So let me just kind of make an observation here. So this is equal to f of b minus f of a for what? Big F of x is equal to 1/2 x squared, right? This one is equal to f of b minus f of a, where what's the big F this time here? Big F of x is so this one, it's c times x, the formula for big F of x. Now, all right, so that's I'm just making an observation. You may or may not see that, pattern, but it's there. Now, can you guys tell me, how does the big F relate to the integrand? How do you get, what operation takes you from this formula right here, right, back to the integrand? And how do we get from this formula back to this integrand? What is it? What operation is that? Yes, it's the derivative. Yeah, these are just, so the derivative of big F is the integrand, right? So what that means in our new language is that the big F is an antiderivative of the integrand. The fundamental theorem of calculus part 2 simply says that it's not an accident for these two examples. This is a general truth. That's the fundamental theorem of calculus part 2. What's that? This is the fundamental theorem of calculus part 2, FTC 2. FTC 2, if big F prime of x equals to little f of x, then the signed area, the integral from a to b of little f of x dx is equal to f of b minus f of a. All right? Now, is what I have on the board a proof? Certainly not, right? This is just a pair of examples that points out a pattern. All right? Now, the other fundamental theorem, there's actually there's two commonly held fundamental theorems of calculus, but I teach a third one for your convenience. And so let me try to give you a discussion of it here. So what's an area function? I should define what we mean by area function. So the definite integral is an example of an area function, but it's not the only one. I mean, well, anyway, here's what we mean by area function. We say let a of x, what's that going to be? That's going to be well, let's say signed area actually, why am I doing that? You need not be stupid. I can give you a formula. A of x is the integral from a to x of f of t dt. So just to draw a picture, you pick a point A, right? And you look at the function, I don't know what it looks like, whatever. And then like a of x, if this is x, then a of x is the area, signed area up to from a to x. All right. So let me take my picture here and just kind of keep going a little bit. All right, say I go from x to x plus, let's say, dx. Right. If I go just a little bit further, or if you want, I could use a delta. Let me use a delta x just to be less. I'll use dx, x plus dx. Why not? Then this little bit of extra area we could call dA, or you could call it delta A if you wanted to be more finite. What's the extra bit of area there? How is it related to the function? See, this is the graph y equals f of t, and this graph. I'm using t as that axis there at the moment, because I'm thinking of x as the fixed point that we're discussing. So I don't also want to use it as the variable. So you guys tell me, what's the area? What's the formula for dA here? This bit right here, in terms of, this height right here is f of x, right? And since this is an infinitesimal, this is really, really tiny, this height and that height, they're almost the same despite my picture. So what's the formula for dA? Well, dA is straight up f of x. That's the height. The width from x to x plus dx is dx, right? So what does this suggest about dA dx equal to? So this suggests that the area function, the derivative of the area function, right, should be the integrand. And that, my friends, is Fundamental Theorem of Calculus Part 1. So FTC I, it says the following. It says that the derivative with respect to x of the area function, the integral from a to x, f of t dt, equals to f of x. That's FTC I. The more nuanced statement of it is in my notes. It's really a statement about the existence, the differentiability of it. And so like in the notes, if you read the proof of this, and I don't think I'm going to go over it in class because honestly, I've been thinking about it as we're sitting here. And we lost that class due to the weather. And I think it's pretty much, I thought we had more time than we did, say Monday. But now that I look at the schedule, I realize we're down a day. So I'm going to have to omit the proofs of these. My apologies. I do like to prove these in class, but I think you're probably better served by me doing examples of them as opposed to going through the proofs. I'll do one proof, But there's a separate proof of FTC1 and also actually once you have FTC1, you use FTC1 to prove FTC2. There's actually a way to prove that with this. It's about 3 lines. But the proof of FTC1, it is a squeeze theorem argument. You actually calculate the difference quotient for the area function, and it's strongly based on using the properties here that I just erased. It's about a page. It takes me about a half hour of class to do it justice. So maybe I'll add a video of it if you're interested or something like that. That sounds like a good idea. Optional video of proof. Yeah, we can do that. Okay, so now for FTC3. So this is what I call FTC3, which is just this is just me being silly. No one else calls it FTC3 as far as I know. But if you calculate the derivative with respect to x of the integral from a as a function of x to b as a function of x, f of t dt, that ends up being f of b of x times db dx minus f of a of x times dA dx. So this is really nothing more than differentiating FTC2 and applying the chain rule. So if you can imagine a and b not being numbers but being functions, then you could apply the fundamental theorem of calculus part 2 at an infinity of points and then take the derivative of that and get this. But again, I really think of this as just as a consequence of FTC2 with the chain rule. For example, let me show you an example. So if we were going to differentiate with respect to x, say the integral from x squared to x cubed of inverse hyperbolic tangent of the square root of t plus 7. All right. Well, that's a very scary question unless you have understanding of FTC 3. Because the thing is, we do not have the tools to calculate that antiderivative, right? We can't actually perform that integration. I'm not sure even after a full semester of Calculus 2, it's something we can do. Probably not, actually. This is probably too nasty. But that's not a problem because we just say, okay, well, this is f of t, right? It's my f of t, and so what I do is I do f of x cubed times the derivative of x cubed, which is what? 3x squared, right? Minus f of x squared times the derivative of that, which is 2x, right? So I have to evaluate the integrand at x cubed. So I've got inverse hyperbolic tangent. Let me write the 3x squared first. 3x squared inverse hyperbolic tangent of the square root of what was t here? X cubed. Square root of x cubed plus 7 minus 2x inverse hyperbolic tangent of the square root of x squared plus 7. And there you go. That's about as bad as it can get, right? I'll do one more example. Calculate the derivative with respect to x, so say the integral from say x squared to 3 of, we'll do cosine squared of e to the t plus pi there, dt. So again, we just identify this is my integrand f of t, right? and apply FTC3. FTC3 tells me f of 3 times ddx of 3, right, minus f of x squared times ddx of x squared. And so derivative of 3, that one's easy, right? 0. And derivative of x squared is 2x. So we get minus 2x cosine squared of e to the x squared plus pi. And there you go. That's all there is to it. Don't forget that there's likely one of these on your third test, all right? But it's also very likely that I don't revisit this topic again in lecture. I'm going to spend all of our time on FTC2 and its application, because that's what's more important, all right? Like, there exists an application somewhere which uses this kind of differentiation. In the study of optics, there's something called a Fresnel function, which ends up being like the integral. There are places where in applications you end up defining a function in terms of an integral, and then if you're interested in calculating the rate of change of some function like that, then you need to do this kind of differentiation, but it's kind of a rare problem. Okay, so I think I said I promised you a proof, and so here is the proof that I was going to give you. Of all the proofs in my notes, this one is the one I think I would call constructive. It actually gives you perhaps some window as into why FTC2 happens to be true. All right, so, and it's actually almost a direct calculation. So here's a proof of FTC2. And so, we suppose A equals to x naught, right? And B is equal to xn, x sub I, I'll say x of j, is equal to A plus j delta x. And what's our delta x equal to? Like last time, delta x is B minus A over n. So set up the partition like usual. Suppose that f of x has antiderivative big F, all right, of x for a less than or equal to x less than or equal to b at least, all right? So apply the mean value theorem on the subinterval x sub j minus 1, comma x sub j. That's the jth subinterval. What does the mean value theorem say? Well, we have an antiderivative, the big F, right? It is differentiable, right? And so what does the mean value theorem say for the antiderivative? It says that the average rate of change of big F is equal to the instantaneous rate of change of big F over that subinterval, right? So what it says is that big F of x sub j minus x sub j minus big F of x sub j minus 1 divided by the width of this subinterval. What is the width of every subinterval? By construction, it's delta x, right? X sub j minus x sub j minus 1 is delta x. So this is delta x. The mean value theorem says that this is equal to f prime of what? Of some point. Let's call it x sub j star. Right? Where x sub j star is where? It's an element of x sub j minus 1 to x sub j. It's somewhere in there, right? That's the mean value theorem. But can you guys tell me, what is big F prime? in this discussion. Remember, it's the antiderivative of the integrand. The antiderivative, I said suppose little f of x has antiderivative big F, right? So that means that this f prime is little f, which means that this is equal to f of x sub j star, right?
So if big F x, then f prime of x is the term f.
Right. Big F is an antiderivative of little f. So that means when we differentiate big F, we get little f by definition of antiderivative. But as it interfaces with the mean value theorem, it means that this change in big F divided by delta x is equal to that, right? But algebra then says that this f of x j star times delta x, right, is equal to what? It's equal to f of xj minus f of xj minus 1. Which is a curious formula, right? Because this is what? This is the area of the jth approximating rectangle. And on the other side, we have a difference of the antiderivative on the endpoints of the subinterval, right? So we can straight calculate the Riemann sum using the points given to us by the mean value theorem. So sum j equals 1 to n of f of x sub j star. I'm going to use the points given by the mean value theorem to select for the sample points of the Riemann sum. And what is that? Well, we can write that more explicitly, right? That is I forgot to pan over to that. My bad. So this is explicitly, I'll write it out. This is f of x1 star delta x plus f of x2 star delta x, f of xn minus 1 star delta x, and so forth, right? F of xn star delta x. But what is this? By this, what we just did down here, that's f of x1 minus f of x naught, right? What is f of x naught? That's a, right? The next one here, that's f of x2 minus f of x1, right? Plus f of xn minus 1 minus f of xn minus 2. And then finally plus f of xn, which is b, minus f of xn minus 1. All right? And what's happening? This cancels with that, right? This cancels with something that's in here that I haven't written, but it's there, right? This one cancels with that one. This one cancels with something over here that I haven't written. All that you're left with are those two terms. And so that's why the Riemann sum is equal to f of b minus f of a. Now, and of course, as n goes to infinity, you still have f of b minus f of a. Now, there's something that somehow there's a cheat in here, right? Because it's not true. I don't know, maybe it's true. I think it's true, actually. So anyway, this, taking the limit as n goes to infinity, we obtain So that gives you, I think, some sense of how it is mechanically that this theorem's happening. It's some kind of sneaky cancellation involving the antiderivative. And it's intimately connected to the mean value theorem in this way. But anyway, as I told you guys, this is a mystery that this is true. All right, so let's spend the rest of class doing examples. All right, let's start out with something relatively simple. Let's calculate the area under the first part of the sine function, right? Like, let's find the area here. What's this area? Whoa. So this is pi, right? So how do we calculate the area? We use the definite integral, right? We need to calculate the integral from 0 to pi of sine of x dx. So what's the antiderivative of sine? All right, so every one of these problems, we're going to use FTC II. We're going to do the integral from a to b of f of x dx is equal to f of b minus f of a, where big F prime of x is equal to little f of x, right? This is our tool. So you said, what was the antiderivative of sine? What was it? Negative cosine? Very good. So we have minus cosine of x evaluated from a to b. Aha, I've just introduced a new notation. So by the way, this difference, a way you can denote that is big F of x evaluated from a to b. See that? This is the integration evaluation bar. This notation is just a shorthand for this difference. So when I write cosine of x from a to b, well, first of all, I shouldn't write a to b. What's my a? A is 0. My b is pi. All right? So we've got minus cosine of pi minus a minus cosine of 0. So I'll remind you, cosine of pi is minus 1, right? And cosine of 0 is, cosine of 0 is 1. So this is minus a minus 1, which is a weird way of saying 1 plus 1. So the answer is 2, yeah. Is that hard? This is not hard, right? People should not. What's that? Well, okay, you mean the knowing cosine of pi is minus 1? Well, I mean, you guys do get calculators and such, but I mean, you're allowed to bring one. But, I mean, it is, you really do want to know what cosine of pi and cosine of 0 is by off the top of your head anyway. Like, the process of picking up a calculator and plugging that in is slowing you down, like way, way down, you know, as you go on in math. Because cosine of pi and sine of pi, these things continue to come up in calculus 2 and calculus 3 and in differential equations, you know, so. But anyway. How about this? Example 2. Let's calculate the integral from 1 to 3 of the square root of x plus x cubed. All right, so how do we do this? We need to figure out what is the antiderivative of this expression, right? No, what's the antiderivative of the integrand? So if this is f of x, then what's big F? So in your quiz, remember, I told you that the integral square root is 2/3 x to the 3/2. Now, you can check me on that. If you differentiate that, you pull down to 3/2, that cancels the 2/3, and you're left with x to the power 3/2 minus 1, which is x to the power 1/2. And doodly doodly, the derivative of that is square root of x. So you can believe me. What's the antiderivative of x cubed? You guys can do that one. That one's easier, right? The antiderivative of x cubed. Three x squared would be the derivative of x cubed. 1/3 x is in the right direction, but it's not 1/3. So remember, integral of x to the n dx, 1 over n plus 1, x to the n plus 1, plus a constant, right? So we do add 1 to the exponent, which is 4, and so we have to divide by that. So 1/4 x to the 4th. If you said that and I didn't hear you, my apologies. I sometimes miss what people say. No, okay. And then we have to evaluate that thing from 1 to 3. All right, so great. That's 2/3, 3 to the 3/2 power, plus 1/4, 3 to the 4th power. I usually put parentheses to keep myself honest. Parentheses are your friend here. Minus 2/3, 1 to the 3/2 power, plus 1/4, 1 to the 4th power. And we should clean that up a little bit. That's 2/3. Well, I'll just leave it as 3 to the 3/2. I mean, you could simplify that further and leave it 3 to 3/2. And 3 to the 4th is what? It's 81, right? So plus like 81 over 4. I left my calculator in the office, my apologies. And then this is minus 2/3 plus 1/4, which I guess I could make into a common fraction. But I'm going to be lazy and just leave it here. For the sake of me not going nuts in grading, on occasion I'll ask for a decimal answer for a definite integral, just so I can not get lost in people's way they present the number here. But anyway, not plugging in the numbers correctly into f of x, this is like a 10%, 20% deduction, right? That's part of the problem, right? But it's not the biggest part. The biggest part of the problem is really understanding that you have to use FTC II and also knowing how to anti-differentiate the integrand. That's the major skill here that you need to get comfortable with, right? Example 3. Let's calculate the integral from the natural log of 3 to the natural log of, 10 of e to the x dx. By the way, can you tell me geometrically what the last example means? What is this number? This number is the area, right? The signed area bounded by y equals square root of x plus x cubed for 1 less than or equal to x less than or equal to 3. And by the way, as a gut check on your calculation, when you get a number which is positive or negative for a definite integral, you should always ask yourself the question, does that make sense? Like this one, is this a positive number? I mean, it's kind of hard to see because it's not simplified, right? But this first term will dwarf the second, right? This is definitely a positive expression. And that makes sense because this is integral. The integrand here is a positive function from 1 to 3, right? And that properties of definite integrals, one of the things we had was like f of x greater than 0 means the integral of f of x is greater than 0, right? And so we should expect that this is positive because we're integrating something positive. This one here, what we got? What's the antiderivative of e to the x? E to the x plus c. Okay, I'll even add the c. And I'm going to add the c this time because why didn't I do it the last couple times? I mean, why wasn't I worried about it? Let me show you why. So this is e to the log 10 plus c, right? Minus e to the log 3 plus c. See what happens with those c's? They cancel out. So for the application of anti-differentiation for the FTC II, like adding a constant thing, it doesn't matter. Like they cancel out. So I always just ignore them, just because it's going to cancel. So why not use the one without the plus a c? And so this is what? 10, 3, 7. What this means is if you look at the graph of the exponential, all right, between the natural log of 3 and the natural log of 10, the area, the signed area bounded by y equals e to the x in here is 7. It's kind of neat. One last example here. What if we did the integral from 0 to 2 pi of cosine, I'll use theta this time, theta d theta. So let's see here, integral of, I'm going to write it this way, integral of cosine theta d theta is equal to the sine of theta plus a constant, right? That's the indefinite integral. So I can use FTC II. Integral from 0 to 2 pi of cosine theta d theta is sine theta plus a constant, which I'll just use sine theta, evaluated from 0 to 2 pi, which is what? We got sine of 2 pi minus sine of 0. What's that? Here's a picture of what we're doing. Here's a picture of what we're doing. This is cosine from 0 to 2 pi. So what's going on here? The signed area is 0. Because you've got equal positive and negative over the full cycle of cosine. And that's why this is 0 minus 0. The answer is 0. So anyway, thanks guys. I'll stop there. I don't want to take too much of your time. So anyway, so Friday we have lab, and I'll try to take homework. If you have any remaining homework questions Friday, I'll try to leave a half hour Friday for that. All right.